Hello, and welcome to today's presentation, which is entitled Responsible AI in Official Statistics with the Model Context Protocol. We are beginning to see a major shift in how people look for data. Instead of browsing a portal or downloading a spreadsheet, users treat conversational AI systems like search engines. If you ask for the population of England from the 2021 census, the system runs a quick web search, pulls the data, and gives an instant, well-written answer. In this simple case, the numbers are right. It's completely frictionless, and that builds user trust very quickly. But what happens when the questions get harder? For example, can you show me how many young mothers there were in different regions of England and Wales in 2017? Answering this requires a multi-step operation, not just a text lookup. The system has to define young mothers, locate the right dataset, match the year, match the geography, and extract the right values. Now the data definitely exists. A human analyst can go right to the ONS Nomis platform, click through the dimensions, check the metadata, and find the exact table. For instance, the platform shows there were exactly 2,856 mothers under 20 in the Northwest. And the question is, can the AI system find it and read it correctly? When we ran this prompt through Google AI, the response looked perfect. It identified young mothers as those under 20. It gave a clean regional breakdown, cited official ONS sources, and used professional language. Most everyday users would accept this without a second thought. But look at the value for the Northwest, 3,099. The data on Nomis was 2,856. In fact, all the values are wrong. They don't match any values in the quoted sources either. When I asked the AI exactly where it got the data, it gave a highly confident response and pointed to a specific ONS live births landing page. But if you go to that page, the 2017 dataset just doesn't exist there. The spreadsheet series ends at 2016. Because the search tool pulled a landing page instead of a data file, the model simply filled in the blanks. It invented a realistic table structure, populated it with fake numbers, and described a methodology that never happened. And when asked about the missing file, the system immediately apologizes and admits it hallucinated the data. But out in the wild, regular users don't run these verification checks. The clean interface makes unverified numbers look like absolute truth. And this is the core issue. Language models are excellent at text, but they are not database engines. They struggle with complex tables, truncate large files, and smooth over missing details with realistic guesses. We can't change how these models work, so the data has to be delivered to them differently. And this leads to a fundamental question. If AI becomes the default interface to access information, what are the implications for the publication of official statistics? For decades, statistical agencies have designed data dissemination for human eyes: websites, portals, and downloads. But today there's a new consumer: machine systems acting on behalf of humans. If data is only accessible via human-centric web interfaces, then these systems will default to web scrapers and guesswork. Official statistics have to be made AI ready. And to see what AI ready data looks like, we can look to the Open Data Institute's framework. The ODI breaks this down into three areas: dataset properties, metadata, and the surrounding infrastructure. The takeaway is that data must be clean, consistent, and served in structured formats with rich metadata. We need to move past static web pages and build a predictable foundation so AI systems can find and use the data directly. And this matches the UK government's guidelines, which outline the 4 pillars of AI-ready data: technical optimization, data and metadata quality, organizational context, and legal and security compliance. There's a clear overlap with the ODI model. Making data AI ready doesn't mean rewriting statistical standards. It means optimizing how we deliver it. We need efficient API access, high quality data, and clear business logic so AI systems can query numbers accurately and safely. Our product Cantabular allows users to build privacy-protected cross-tabulations from sensitive microdata. In many ways, Cantabular is already AI ready. It has a robust API and structured metadata. The challenge is making that interface accessible to an AI system. The diagram highlights a big gap in step 3. How does the AI actually execute that query? And the rest of this presentation is about how we fill that gap. And the exact same principles apply to any other machine-readable statistical interface. Well, we fill that gap by leveraging a capability built into modern LLMs, tool use. Tools are simply external functions or APIs that we describe to the system in plain text. Modern LLMs have been explicitly trained to recognize these descriptions and use them. Instead of just generating prose, the model is trained to analyze a prompt, look at the available tools, and output a structured command, like a JSON payload, to trigger an external application. And we saw an everyday example of this earlier with the web search. The model recognized that it lacked the 2017 data in its training material, so it triggered the search tool. We can define those exact same tool interfaces for a system like Cantabular, allowing the model to bridge the gap and execute a precise statistical query instead of guessing. And if AI systems are going to use specialized tools, they need a standard way to connect to them. And that's where Model Context Protocol, or MCP, comes in. It's essentially the USB-C for AI tool integration. Before this protocol, exposing a data tool to an AI meant writing custom, fragile code for every individual platform. One integration for ChatGPT, another for Claude, and another for VS Code. MCP replaces that with a standard open contract. A data provider hosts an MCP server, and any compliant AI platform can automatically discover what tools are available, see what inputs they need, and run them securely. The big benefit here is reusability. You build the tool interface once, and it works across the entire AI ecosystem. The protocol clearly separates the architecture into clients and servers. At the top you have the MCP clients, which are the AI applications like ChatGPT, Claude, or VS Code that want to use data and tools. At the bottom are the data and tools themselves, things like your databases, files, and APIs. The MCP server sits right in the middle. It acts as a consistent interface, exposing capabilities and handling requests so that clients can talk to different backend systems in a completely standardized way. There are two main ways to deploy an MCP server, local and remote, and both provide the exact same interface to the AI system. Local MCP runs directly on your device, accessing local resources. This is used for developer environments, standalone setups, or workflows that require strict data isolation. Remote MCP runs in the cloud or on a centralized network, connects over HTTP, and allows data tools to be securely shared and managed across multiple users and systems simultaneously. We're already seeing implementations from major statistical and development organizations. India's Ministry of Statistics hosts a live, public, remote MCP server for querying national data. Meanwhile, the World Bank and the US Census Bureau have published open source repositories. Users can run these MCP servers locally on their own devices, and the servers handle connecting to the organization's public data API over the web. These groups are adopting the protocol to provide a standardized pathway for AI applications to interface with their data. And we wanted to show some actual code here just to demystify how this works. An MCP server is essentially the interface layer between the AI system and another backend system, like a database. By using the official Python MCP package, the code stays incredibly small because that package handles all the underlying communication for us. In this basic example, the script just exposes a single tool that uses standard SQL to look up a list of datasets in a database. Now, a real production server for official statistics would be a lot more complicated, but the core pattern is exactly the same. The MCP server acts as a strict boundary, telling the AI exactly what it is allowed to ask for and passing the data back safely. And here it is running inside a client. The user asks a question. The system checks its list of tools, selects the right one, sends a structured request, and gets back exact data. It shifts the model from guessing answers to executing reliable code. But of course, this is still an emerging standard. It requires explicit configuration, and it brings security concerns like prompt injection or unauthorized tool calls. For statistical agencies, this means implementing robust infrastructure, clear permissions, and full audit logs. Using the same principles I've just outlined, we built an MCP server to make Cantabular accessible to AI systems. We implemented a set of tools that lets an LLM discover which datasets are available, explore the metadata, and request data. Cantabular uses the exact same privacy protections as always, and never grants access to raw microdata. Cantabular remains in full control of data safety and disclosure at every step. Let's see this in practice. For this demo, we've taken official life events data from Nomis, including the birth dataset we looked at earlier, and we loaded it into Cantabular. We then set up an MCP server over HTTP to connect to that interface. Over in ChatGPT, I've configured the settings to link directly to this remote server. This gives the LLM immediate access to the tools it needs to communicate with Cantabular. When I start a new chat, I enable the MCP server. Now I can ask a straightforward question. What datasets are available in Cantabular live events? Now, because this is a live demo interacting with a remote LLM and server in real time, we might see some brief pauses while the systems talk to each other. But now let's come back, and under the hood, ChatGPT has checked its available tools, recognized our server, and queried it to see what's hosted. It then takes that raw data and lists out the available datasets for us. So we've got a couple of datasets on live births, one in divorces, and a couple of datasets in marriages. Now let's ask what variables are in the live births by characteristics of mother dataset. ChatGPT has returned a list of all the variables in that dataset. And if we look at the tool call, we can see exactly what happened under the hood. Even though the name I type is slightly imprecise, ChatGPT mapped it to the correct asset and triggered the Get Dataset Variables tool. The server then returned raw JSON list of variables, and for each variable, we've got a description, label, and name. And ChatGPT then uses this as context to build its response. Now let's revisit our question about young mothers in 2017. I'll ask how many young mothers were there in different regions in 2017. ChatGPT handles the orchestration automatically. It identifies the right dataset, finds the correct variables and categories, and queries Cantabular for the specific counts, presenting them in a nice table. And we notice the count here for the Northwest of 2,856, which is the same value as earlier. ChatGPT also pulls through relevant methodology notes, and it provides a link to the data back in Cantabular. And we can use that link to see that the values provided by ChatGPT match the values in Cantabular. So for the northeast, we get a value of 1333, 2856 for the northwest, 2390 for Yorkshire and the Humber, and so on. We maintain a clean audit trail right back to the source of truth. And as I said earlier, MCP works across different AI systems. Here's a screenshot of Claude connected to a Cantabular MCP server. But notice something else here. This isn't the birth data. It's a completely different instance of Cantabular running an Irish 1911 census dataset. We didn't need to change the underlying code to make this work. We simply configure the MCP server to talk to a specific running instance of Cantabular. The server then reads whatever metadata that particular instance provides. The exact same code works whether it's pointed at modern birth rates or a century-old census. Now this works well for quick queries and small tables. But what happens with a larger table? And this is actually a major focus of our ongoing work. Pushing a massive table into an LLM prompt simply doesn't work. It overloads the context window, and the model can't accurately reason over huge matrices anyway. Even pagination just breaks a bad user experience into multiple pieces. Instead, we are focusing on returning precise slices or summaries. For really large datasets, our approach shifts entirely. The tool shouldn't return the raw data at all, but rather a secure API link or query reference. And this data referencing pattern protects the LLM from data overload, and it changes what the AI can do next. With data links, the AI stops reading raw data and becomes an orchestrator. And this is agentic AI. It takes the data link found via MCP and passes it straight to specialized back-end tools. The processing happens securely on the server, and the AI simply manages the steps. To see how this works, imagine a government analyst using a custom AI agent built for the department and connected to official MCP data servers. If they need to compare regional datasets over time, they don't download spreadsheets, they just ask the custom agent in plain language. The agent uses MCP to locate the data, grabs the secure references, and triggers an analytical tool to run the comparison. The math happens on the server, and the analyst gets a standardized report. Now let's look at a simple prototype of this kind of setup. We built a prototype agent using the AWS Strands SDK, and I've already asked a question about a large dataset. Give me data on the age breakdown of mothers in different regions of England and Wales since 2017. And the agent used MCP to locate the right information. But instead of dumping hundreds of rows of raw data straight into the LLM context, the server returned a truncated table. It says here it's only returned 100 out of 560 cells. It's also returned some explanatory notes and a link to the full table in Cantabular, which we can open again. And this is where the agentic behavior kicks in. The agent has access to back-end tools that can take that data link and process the information much more reliably than an LLM can. In this prototype, it offers the user two logical next steps. It can trigger a tool to generate a full report, or it can provide a Python code snippet so the user can analyze the data themselves. If the user chooses the report option, the agent passes the data link to a backend script. That script uses standard Python libraries to pull the complete dataset, to generate time series line graphs for each individual region, and to compile them into a clean PDF document. The heavy lifting happens entirely on the data server, ensuring the math is perfectly accurate. Alternatively, if the user asks for the code, the agent outputs a clean snippet referencing the direct API URL. And this allows them to pull the data straight into a pandas data frame. Now, these two tools are just examples. In a real-world deployment, an agent could be equipped to generate standardized monthly reports from templates, format charts using exact organizational styles, or scan the dataset for anomalies. The main takeaway is this: MCP allows users to discover data naturally using plain language, while AI agents use secure data links to automate the processing. The LLM handles the orchestration, while the data remains secure and intact on the server. To wrap up, 4 key points. First, generic AI is not enough. Unstructured access risks producing highly realistic but entirely incorrect data. Second, trusted AI needs metadata, APIs, provenance, and safeguards. Official statistics must be delivered through AI-ready interfaces that prioritize these structural elements. Third, MCP enables controlled access. Tool-based frameworks like this keep the AI integrated with deterministic back-end systems, preserving vital disclosure controls. And finally, the Cantabular MCP server is a real working example of this. It shows how AI can safely handle the request rather than letting the model generate numbers on its own. The real goal for statistical organizations is making sure that when these systems answer users, they are pulling directly from a trusted, official source of truth.